Hi, I'm Claudio Tocalli. I work as a software engineer for DNA Algo, and in this presentation I'm going to talk about the error correction codes. So what are ECCs and why do we need them? This is a general problem to information theory communication. There are two separate entities, A and B, and A wants to send a message to B. In this case, the message is formed of 4 bits, 0, 1, 1, 0. But what happens in practice is that there is a noise source which damages the content of the fourth bit. So you see here that the fourth bit has become a 1, has changed its content, its value. So the question here is twofold. Can we know that he received the wrong message, and can he also fix it? So this is related to two properties of an error correction code, which are called detection and correction. What ECCs do in practice is to add a few bits here, a few extra bits, that can be used to restore the original information. And these bits are called redundancy bits or parity bits, and are used to define a very important quantity in this field, which is called code rate, computed as the ratio between the information bits and the total number of the bits we have transmitted. So let's see a couple of simple examples. The first code is called single parity check code. And if we use this code, we just compute one parity bit as the XOR of all the information bits. I recall you the XOR is just the sum modulo 2. So in this case, 0 XOR 1 XOR 1 XOR 0 gives 0 as a result. So this is what A sends. But if we suppose that our noise source, as before, acts on bit 4, B receives the wrong message, and if B computes the XOR of the information bits, he obtains 1. Here, however, B sees a 0, so he knows that something has happened, he knows that something is wrong, so he detects that something has happened, but he has no clue on how to fix it. So detection, but not correction in this case. Also, we see another example, this Hamming 7.4 code. Hamming codes have nice mathematical properties. In this case, 7.4 are two parameters. 4 is the length of is the number of our information bits, while 7 is the total number of data we transmit, so 4 information bits plus 3 parity bits. The nice property of this code is that we can detect up to 2 wrong bits and also correct 1 wrong bit. So let's see what happens in the case we have already seen where the fourth bit has flipped. So in this case, we have 3 parity values which are computed through 3 different equations. These are simply 3 XORs, and they are computed using information bits. So simple XORs, P1, P2, and P3, if you do the computations, are 1, 0, and 0. So A sends this message, which is 7 bits long, 4 information bits, plus these 3 parity bits, 1, 0, 0. But then, if our noise source acts as before, when B tries to compute the values of the parity bits, something happens because these equations are not satisfied. I mean, the second one is correct, but the first one and the third one are not correct. So what we does here is to look at the first and at the third equation, the not satisfied equations, because if there is a component present in these 2 equations but not present in the second equation which is satisfied, well, that's the wrong bit. And what happens is that I4 is exactly what we were looking for. So if we change the value of I4 from 1 to 0, we can compute again these parity values, and we see that now the three equations are satisfied. So in this case, we can restore the original message, which is 0, 1, 1, 0. So the decoding is successful in this case. So not only detection, but also correction. That's it. I hope you enjoyed it.